Hi everyone, today we're starting Unit 8, Acids and Bases. We're going to first start with just a broad introduction to acids and bases. We talked about this a little bit in Unit 8, and we're going to continue that introduction here now. Now first, just some reminders of definitions. We have the Bronsted-Lowry acid-base theory, which is a theory that governs acids and bases. It says that acids are proton donors. As a reminder, proton is H plus ion. And this essentially means it gives up H plus. And a base, or bases, are proton acceptors. Again, proton being H plus ion, this means it takes an H plus. So we're going to start this discussion off on acids and bases talking a lot about water, because water has a huge role to play in acids and bases, and everything we're doing is in water. And so when an acid gives up H plus in water, it doesn't exist for long. And by doesn't exist, I mean the H plus does not exist for long. The reason why is because you can't imagine protons just kind of floating around in water. What ends up happening is that H plus reacts with the water, and that forms, and it's normally in equilibrium, depending on if it's a strong or weak acid, and we'll talk about that a lot more, it'll make H3O plus. This we've talked about before. This is a polyatomic ion. This is hydronium ion. And you can essentially also think of this as meaning acid. So if you see H3O plus, if you ever see this, that means acid. We can also think about this as doing some IMFs, right? And so we can have this hydronium, H3O plus, which is shown right here. This is capable of hydrogen bonding with water. And so this H3O plus dissolves in water, which is why it's aqueous. We can keep this going, right? You can have one of these hydroniums interacting with 3 different water molecules as shown there, or as shown right here. Essentially, the point is, after you make H3O plus, that can hydrogen bond with water. Just a few more things to keep in mind about acids and bases. An acid must have at least one removable proton to donate. And in general, we'll see removable protons as something OH. You'll see H bonded to a halide, right? Those are always acids. And so for bases, these must have at least one pair of non-bonding electrons to accept. So what do I mean by that? I mean, like, if we look at ammonia, for example, NH3, right? This has a pair of, and I'm going to abbreviate non-bonding as NB electrons. You can also think of, for example, water, right? Water has 2 pairs of non-bonding electrons, so 2 pairs of NB. Right, and so it just has to have at least one pair of non-bonding electrons in order for it to actually accept a proton. So for example, if we take, right, CH4 right? This has no non-bonding electrons, so it can't act as a base. Now, of course, we've talked about this a little bit in the past, but water is weird in the sense that it acts as both an acid and a base. And so we can look at this reaction right here. We have NH3. This is ammonia. It's a base. Again, its structure looks like this. So it has a pair of non-bonding electrons right there. This, if I draw out the structure for water, can essentially take that little proton right there, can take that hydrogen away, and this is an equilibrium, and what it makes is NH4. I'm showing these in structure so you can physically see what's happening, right? Now, this has no non-bonding electrons. So after it's taken those electrons, it now no longer has those non-bonding electrons. And now you have OH, which has an extra pair of non-bonding electrons as a result. So this has non-bonding electrons, which is why this is in equilibrium, right? And you're forward, the ammonia, NH3, is using those electrons to take away proton from water, which is acting as your acid. So acid is giving ammonia the water. And then in the reverse, right, this one now has the extra protons, and this one has the non-bonding electrons. And so the exact reverse reaction happens. And so water can act as both an acid and a base. In this case, it's acting as an acid. But we can also think about it in this context. Let's say I have H-Cl plus H2O. This HCl, this is an acid. H2O in this case is acting as a base. And so we make H3O plus and Cl minus. We've talked about this a little bit before too in Unit 4, but two formulas that differ by H plus and only H plus are called a conjugate acid-base pair. And so in this reaction, we have our acid, HNO2. You can see it loses H plus. So it's an acid. If it loses H plus, then the product is the conjugate base. In other words, what started as the acid in the products will become the base, because remember, these are under equilibrium, so they can go forward or back. And then if we look here, our original base, this is water, it gains H plus to become H3O plus. So whatever gains H plus, the product of that is the conjugate acid. So I'm going to write here again. Acids in the reactant become the conjugate base in the product. So if it's an acid in the reactant, it's going to become the conjugate base in the product. And if it is a base in the reactant, then it becomes the conjugate acid in the product. So one will become the other after the reaction. And of course, this is an equilibrium, so it can go in the reverse direction as well. Now again, because water can act as both an acid and a base, something that can happen is called the auto-ionization of water. We call water amphoteric, meaning it is both an acid and a base. And if you react water with itself, it can actually make OH minus and H3O plus. So essentially it ionizes itself. It acts as both an acid and a base to itself to make these two products. Now the reason this is important is because we can think about this in the context of equilibrium. We know before from Unit 7 that Kc is just the concentration of products over reactants. If we look at that equation I just showed, we have H2O liquid plus H2O liquid reacts under equilibrium to form OH minus aqueous and H3O plus aqueous. And so if we want to write this in terms of our equilibrium constant, we know that this and this will not appear because they're liquids and only aqueous species appear. And so if we look, it's products over reactant. So the equilibrium constant here is just the concentration of H3O plus times the concentration of OH minus. This is actually a special K. We call this Kw, which is the ion product constant of water. And we actually know this number, and it's a number that I want you all to remember because we're going to use it quite a bit. Kw, and I'm going to specifically put in parentheses at 25 degrees Celsius, because this is not true at other temperatures, is equal to 1.0 times 10 to the negative 14. And we will use this number to help calculate acidity. It's a constant that helps us understand whether or not things are acidic or basic, and you'll see in the next few lectures how we do that. But it's important that we remember that Kw is the concentration of H3O plus times the concentration of OH minus, and this is equal to 1 times 10 to the negative 14th. Now, a little point of confusion as well that I want to clear up now is this H3O plus, right? We said if you take a proton and add it to water, you get H3O plus. So oftentimes, you'll see that H plus is actually just equal to H3O plus. And so if you see one or the other, what you need to think about is they're saying the same thing. They're saying acid. This is the concentration of acid. Now this is useful because it can be used to figure out the acidity of solution. So let's take the case of my concentration of H3O plus is equal to the concentration of OH minus. That means that the solution is neutral, right? I have the same amount of base that I have of acid. It's neutral. If concentration of H3O plus is greater than the concentration of OH minus, this is acidic because I have more acid than I have base. And if the concentration of H3O plus is less than the concentration of OH minus, this of course means that I'm basic because I have more base than I have of acid. However, you'll notice for any of these, H3O plus, in any case, H0 plus times OH minus is always going to equal Kw, which is always equal to 1 times 10 to the negative 14. So no matter what, it's still going to equal that, even if one is greater than the other. The last thing I want to discuss here as our introduction is the concept of pH and pOH. And so pH, we don't typically think of the concentration of H plus because that's a little bit annoying to do, is a method of reporting H plus concentration. pH is just equal to minus the base 10 log of the concentration of H plus. What this means is that pH of 7, that is neutral. So if a pH of 7, that's neutral. If the pH is less than 7, then this is acidic. And if the pH is greater than 7, this is basic. What I mean by that is that in the neutral, we have the same concentration of acid and base, or in other words, water. Acidic means you have more acid than base, and basic means you have more base than acid in solution. Now, the important thing to remember here, too, is that it is a base 10 log system. What that means is that a pH equals 3 is 10 times more acidic than a pH that equals 4. It's not 1 times more, it's not a little bit more, it's specifically 10 times more. So if you go up by a number, that means it is 10 times more acidic. Now, I also said there's a concept called pOH. And this is essentially just the inverse of pH. Right, if pH is looking at H plus, pOH is the minus 10 log of the concentration of OH minus. And then because you can relate the concentration of OH minus and the concentration of H plus to each other, pH plus pOH actually equals pKW, where pKW is just minus log base 10 of KW. So you can use all of these relationships to figure something out about the concentration of acid and base in solution and whether or not you are a neutral, acidic, or basic. This might be a little bit of a helpful but also confusing graphic here, but you can use it if you would like. You can see here if we have the concentration of H plus, right, you can find the concentration of OH minus by doing 1 times 10 to the negative 14th divided by the concentration of H plus. You can also go the opposite way. You can find H plus by taking 1 times 10 to the negative 14th and dividing it by OH minus. You can find pH by just doing log base 10 of H plus, or you can do 10 to the negative pH to go from pH to H plus. If you want to go from OH minus to pOH, you just take the log. And if you want to go from pOH to OH, you just do 10 to the minus pOH. And then finally, if you want to go from pH to pOH, it's just pOH equals 14 minus pH. And in the opposite direction, it's pH equals 14 minus pOH. All of these relationships are helpful, and I encourage you to get used to using them, since we'll often use them in a lot of acid-base problems. We'll talk about this a lot more in class and kind of go over all of these concepts since it's a lot all at once, but for now, that's all. Thanks, guys.